Hello and welcome back to another Siemens S7-1200 and FactoryI tutorial. In this video and the next few videos, we are going to be taking a look at PID control and how to implement it using Siemens SCL code to control the water level in a FactoryI tank. Now, we could have used one of the standard Siemens PID control blocks provided, but I thought we'd get a better understanding of PID control if we programmed it ourselves. We'll also be taking a very brief look at the Ziegler-Nichols tuning technique, something I was introduced to back in the 1980s while studying for my degree in computer and control systems engineering. Now, we definitely get some interesting results, so stay tuned. Welcome back. Now, to avoid any confusion, this video continues from where we left off in the part 2 water tank level control video, and not the Modbus videos where I got sidetracked, although we could have continued from the part 5 video, but I wanted to reduce the amount of things that could potentially go wrong while developing code, and therefore I thought it best not to include the Arduino and Modbus for the time being. Once we've proven the PID code, then we could include the Arduino in the project if we wanted to. Okay, let's get to it. Now, there seem to be quite a few different algorithms for PID controllers that we could potentially use, although they all seem to be based on either series, ideal, or parallel configurations. And the one I'll be using for this demonstration is the parallel version, which is shown in this diagram. So in theory, there could be a better solution than the one we're using. However, as we will see shortly, it seems to work reasonably well for the water tank example we're using. So before we get into programming this controller algorithm, let's have a look at the completed program in action and see what we're trying to achieve and how well it performs. This is the code we will be programming in the next few videos for the controller, and I've placed it in a cyclic interrupt that runs every 20 milliseconds. I also have a startup program block which resets everything as soon as we put the PLC into run mode. In previous videos, I used the FactoryIO running signal to reset variables, which worked well. So this could be considered an alternative method, which is frequently used in PLC programming. If you can remember from the part 1 and 2 water tank level control videos, we programmed 3 function blocks, namely conversion, set point, and valve control, shown here. Now, I would recommend having a look at these videos should you not be familiar with NormX, ScaleX, and ConvertX, as we will be calling on the first 2 of these operations again in the next few videos. We also have a watch table set up so we can monitor values and enter values for KP, KI, and KD, the respective gains for the proportional, integral, and derivative parts of the controller. In addition, we have a trace set up to see a graphical representation of the water tank level process value over time, and we've also docked all the tags in FactoryIO. So firstly, we are going to view the response with only the proportional gain, and we will set it initially to a value of 20 and select the modify button and dial in a set point on the control panel. Okay, we are now filling, and let's view the trace. We have no disturbance at this point, and we can see the water tank fill valve is open fully. and it closes smoothly when the tank fills up to the set point value I dialed in on the potentiometer. In this case, approximately 217. Okay, let's add a disturbance by opening the discharge valve a small amount in FactoryI. We can now see an error of approximately 4 centimeters, which is a steady state error, meaning the error remains fairly constant at 4 centimeters and the water level never returns to the set point value while we have this amount of disturbance in the system. Let's increase the disturbance a little more, and we see the steady state error increases proportionally to the disturbance. Let's increase the disturbance a third time, and we see the steady state error increases again. Now, if you are happy with your system working in this manner, then proportional control is fine for you. Now let's increase the gain to 30 and see what happens. Let's zoom in a bit on the trace. We need to move the trace over a bit now that we've zoomed in. So let's do that. We now see the error has reduced, but again a steady state error remains. Now let's increase the gain again to see if we get any closer to zero error. This time let's try 41. Let's move the watch table a bit and again move the trace area a little. Now this is interesting. We've now got oscillations, and look at what's happening to the fill valve. It's opening and closing like a yo-yo. Not good. So we can see that increasing the proportional gain alone will never reduce the error to zero. To do that, we need the integral part of the algorithm to be introduced. However, take note of the gain value when oscillations occur, as this is known as the ultimate gain, and the time between the oscillations is known as the period. We'll come back to these numbers when calculating the initial values for Kp, Ki and Kd. So let's stop FactoryI and the PLC and make a note of these values before moving on to view the effect of including integral control has on the stability of the system. So the ultimate gain, Ku, is 41, and the period, Tu, works out to be approximately 6.3 seconds. Now let's start the PLC again so that all the variables are reinitialized to 0 when we put the PLC into run mode again via the startup OB100, as we can see here. Let's also start a new trace, so delete the old one and prepare for a new one. As you can see, we are still getting readings of total error on every scan, as this is the accumulation of the scaled error used for the integral part of the algorithm, and we will see why that is happening when we get into programming. Now I'm going to change the value of the proportional gain to 18 and include a value of 3 for the integral gain, Ki. Then I'll stop and start the PLC to zero the errors. Oops, what I should have done is start FactoryI before starting the PLC up again for the errors to reset. So let's do that. Okay, now we are back to 0 and can start the system. Let's accept the new gain values for the PI controller and dial in a set point on the control panel and see what happens. OK, the fill valve opens to its maximum and the tank starts to fill towards the set point value. Now let's start a new trace. As we can see, we overshoot the set point and then the value gradually stops to a level in the tank of about 230 centimeters. This is why I would not have a set point greater than 225 centimeters, otherwise there is likely to be an overflow of the tank. Okay, let's introduce a small disturbance and see what happens. Now we can see that the PI controller reacts and the water level reduces gradually down towards the set point value in a smooth, controlled manner after an initial undershoot. It will eventually get there, but let's increase the disturbance again. Now we see the PI controller reacts again by opening up the fill valve a little more to counteract the disturbance, and the water level still makes its way slowly down towards the set point value. This is very unlike the proportional controller that would never get there. So we can see using a PI controller as opposed to a proportional controller eventually gets to the set point. Let's increase the disturbance once more. And we can see the PI controller reacting so that the water level again goes towards the set point in a controlled manner. Right, let's see how the PI controller reacts to a lowering of the set point. The fill valve closes temporarily. Let's move the watch table out of the way. And then the fill valve opens gradually as we get closer to the new set point value. We now get a little bit of undershoot as the water level goes below the set point value. And as the PI controller slowly reacts, the fill valve opens to counteract the disturbance, and eventually the water level rises gradually towards the set point. Let's just monitor it for a while and see the value increase. Okay, let's reduce the disturbance and see what happens. As we were quite close to the set point value, we got a small peak in the process value and then a smooth transition towards a set point value. The control panel LED is showing 121 at this point, as it displays an integer value of PV real, because PV real is presently greater than 120.5. Now let's increase the set point again quite a bit and see how the controller reacts. This time we have a disturbance, so let's see what happens. The fill valve opens completely for a while, as we can see. Let's just monitor it for a while and see the value increase. Again, we get an overshoot, probably not quite as much. And then the PI controller reacts to stabilize the water level and gradually takes it down to the set point value in a smooth, controlled manner. Let's monitor this for a while again. The level is going down gradually, as we can see. on the control panel LED display. Let's see the watch table. Oh dear, it seemed to freeze for a while. Ah, it's going again. Right, let's stop FactoryIO and the PLC and now add in a derivative. Normally a small amount of derivative would dampen the overshoot, but in the case of the water tank setup like this one, we will see that it has a limited effect and in some circumstances can make the system unstable. In my opinion, as we will see, I don't believe the derivative is necessary with this particular water tank setup, but I thought I would include it for completeness. As you can see, I've made the same error again. I should have restarted FactoryIO before restarting the PLC. Anyway, let's do that now. Okay, the watch table is now zeroed. By the way, the value you can see in the watch table for T is the time constant used for the integral, which is the same value for the cyclic interrupt. Right, we're ready to start the system again. Let's just add the gain value of 0.02 for the derivative and modify the data. Now let's dial in a set point. About 155 centimeters is fine. The tank starts to fill. And let's start a new trace. As we can see, the tank stops filling a little abruptly. Of course, we could do more tuning to improve the situation, but I'm not sure we can better it much more if using a derivative. With no disturbance, we again get an overshoot, so let's increase the set point and see what happens. Oops, I increased it, then reduced it again. No problem. I'll increase it. Again, a bit choppy or turbulent. Okay, let's add in a small disturbance and see what happens. The controller reacts and starts sending the water level gradually down towards the set point value. Let's just monitor it for a while again. Let's increase the disturbance a little. Now let's see what happens when we increase the derivative gain to 0.5 and see what happens. Let's monitor this for a while again. I'll increase the disturbance a little more. As we get close to the set point value, we get erratic oscillations, with the fill valve opening and closing constantly. This is not ideal. The trace shows how bad this really is. So let's reduce the derivative gain back down to 0.02. and as we can see, the controller reacts and the water level settles towards the set point value. Okay, let's reduce the disturbance and see what happens. And as we can see, the water level increases and then the controller kicks in and gradually brings the water level back down towards the set point value. Let's increase the disturbance again and see what happens. As you would expect, we get a little undershoot and then the controller reacts and gradually sends the water level towards the set point. Great. As I said before, we might not have the most suitable controller algorithm here, and I might explore alternatives in another set of videos sometime in the future. But for now, I hope you get the general idea. Okay, that's it for this video. So let's stop FactoryIO and the PLC, and in the next video we will start programming the proportional controller before we move on to the PI controller, then the PID controller. Thanks for watching. Hope you got something useful out of it. If you would like to learn more, then please click the subscribe button and the bell so you'll be informed as soon as a new video has been uploaded. Please see the links in the description should you wish to get a free 30-day license for FactoryIO, and also check out my Patreon account. And I'll see you in the next video. So bye for now.